Hello and welcome. Today you will learn about the concept of countably infinite versus uncountably infinite, as well as why it matters. To understand countable versus uncountable, we need to talk about cardinality. The cardinality, or more informally, size of a set, is the number of elements it has. So if the set A contains 1, 2, and 3, it has 3 elements, so its cardinality is 3. If B contains 10, 20, and 30, then the cardinality of B is also 3. So obviously A and B have the same cardinality because they both have 3 elements, but how else can we show that they have the same cardinality? Well, we can pair 1 in A with 10 in B, 2 in A with 20 in B, and 3 in A with 30 in B. And notice that each element in each set is paired with exactly one element in the other set. And this is called a one-to-one correspondence. So A and B have the same cardinality if there exists a one-to-one correspondence between the elements in A and the elements in B. For finite sets, this is pretty intuitive. And this has been generalized to infinite sets as well. An infinite set is countably infinite if there exists a one-to-one correspondence between its elements and the set of natural numbers, and an infinite set is uncountably infinite if no such correspondence exists. And note that the term countable is not the same as countably infinite. It means either finite or countably infinite. So people often mix these two terms up. Are the integers countable? The answer is yes. We can let A be the set of natural numbers and B be the set of integers, and we can pair 1 in A with 0 in B, 2 in A with 1 in B, 3 with -1, 4 with 2, 5 with -2, 6 with 3, and so on. And notice that every natural number is mapped to exactly one integer and vice versa. So this is a one-to-one correspondence. And since a one-to-one correspondence with the natural numbers exists, the integers are countable. Now, what about the positive rational numbers? This one's more tricky, but the answer is still yes. Remember that a positive rational can be expressed as A over B, where A and B are natural numbers, so we can write them down in a 2D table, with the rows representing the numerator and the columns representing the denominator. And now how can we enumerate this? Well, we can label the top left element 1 over 1 as 1, and then we can label the next element 1 over 2 as 2, and then continue diagonally down and to the left. So the next element would be 2 over 1, which we label as 3. And we continue going diagonally down to the left. So we would label 1 over 3 as 4 next. And the next would be 2 over 2, but this is a repeat of 1 over 1, so we just skip it. And then we have 3 over 1 next, which is labeled as 5. And we continue this process, going diagonally down and to the left. 1 over 4 is labeled as 6. 2 over 3 is labeled as 7, and so on and so forth. And notice that we're going to reach every positive rational number eventually by doing this process. So every positive rational number is mapped to exactly one natural number and vice versa. So therefore, the positive rational numbers are countable. And now, are the rationals countable? Yes. So we just saw that the positive rationals are countable. We can enumerate them as x1, x2, x3, and so on and so forth. So the negative rationals can be enumerated as negative x1, negative x2, negative x3, and so on. So we can enumerate the rationals as 0, x1, negative x1, x2, negative x2, and so on and so forth. By doing this, we're going to reach every possible rational number eventually. And now, are the real numbers in 0 to 1 countable? The answer is no. Regardless of how we try to enumerate the real numbers in 0, 1, we can always find a real number in that interval that's missing from the enumeration. How can we do that? By using Cantor's diagonal argument. So suppose that there does exist an enumeration of the real numbers in 0, 1, such as 1 maps to 0.7389 ... and there's ... because there could be infinitely many digits, and then 2 maps to something else, 3 maps to something else, and so on and so forth. And we can find a new real number x in 0, 1 that differs from the nth number of the enumeration in the nth decimal place. So the first decimal digit of the first number is 7, so x would be equal to 0 and we choose any digit other than 7. So for example, 0. All right, and then the second decimal digit of the second number in the enumeration is 0. So we pick any digit other than 0, such as 1. The third decimal digit of the third number in the enumeration is 5. So we pick a digit other than 5, such as 0. And we continue this process and notice that since x differs from every number in the enumeration in at least one decimal place, it is not equal to any of the numbers in the enumeration, and therefore x is not in this enumeration. So we found a real number in 0, 1 that is not in this enumeration, and therefore the real numbers in 0, 1 are uncountably infinite. We've covered the most important examples of countable and uncountable sets, but if you're curious, here are some more examples. Pause if you want to look over them. So why does countability matter? It may seem like an abstract concept similar to complex numbers, but just like complex numbers, countability has a lot of practical applications. In one of my other clearly explained videos, I go over random variables and how to determine whether they're discrete or continuous. And discrete random variables can take on a countable set of possible values, while continuous random variables can take on an uncountable set of possible values. And determining whether a random variable is discrete or continuous is very useful in analyzing this behavior. In computer science, it can be used to prove that there are impossible tasks. For example, the set of all functions from natural numbers to natural numbers is uncountably infinite, but the set of all possible computer algorithms that can be written is countably infinite. And that means that there are functions which do not have a possible algorithm that computes them. And in math, it can be used to prove many shocking results, such as every countable set of the real numbers has Lebesgue measure 0. Roughly what that means is if I gave you a string of arbitrarily small length, such as 0.001, and allowed you to cut it up into arbitrarily small pieces of positive length, then using that little piece of string, you could cover all the rational numbers on the entire number line. Shocking, isn't it? But it's true because the rationals are countable. And there are also many other fields that can use countability. Thanks for watching. Make sure to check out the rest of my channel where I have a large variety of content, including full AP courses and impressive multitasking challenges. Subscribe for more free content. It also helps out a ton, even if you're not often able to watch my videos. Have an awesome day and goodbye.